Okay everyone, let's look at another example where we're having to calculate the centroid. Now this time, things are both harder and a little bit easier. They're harder because this is a much crazier shape, but they're easier because, well, there's an axis of symmetry, which means that my centroid is somewhere along that axis. Or effectively that, if we're talking about the x direction, I know that my x bar is actually equal to 0. It's just going to be right on the axis. Okay. So I only have to calculate it in one direction, which is going to save me a little bit of time. I'm still going to have to figure out how to break this into some simple shapes. Now, luckily for me, they showed me that this little right here, these lines right here are saying that this is symmetric. It's also showing me that this is like kind of like a big rectangle. So my first shape is going to be this big rectangle right here. Okay, so that's looking pretty nice. And so I'll go ahead right over here, rectangle. Let's call it rect. And I've got those two triangles on the bottom. So I'll just call them triangle 1 and triangle 2. And I've got this little half circle up here. Okay, I'll call that semi for semicircle. And I want to add them all together. Okay, so this is looking pretty good. So let me go ahead and start calculating all the areas and the centroids of all these points. So let's make our little table. I need the area, I need their y squiggly hat, and I need to multiply those two together. Beautiful. And if I have all those, I am golden. Now these are going to be much bigger numbers because I'm working with millimeters rather than feet or inches or something. Now first off, let's get that rectangle's area. So that'll be 200 times 300, which will be 60,000, I believe. 60,000. Okay. Then triangle 1 has an area of 1/2 base times height. So that's 150 times 70 divided by 2. And rather than try to do that in my head, I'm going to get my calculator out and see if it can help me out. So 150 times 70 divided by 2, 5,250. That'll be the same for both of these triangles. Remember though that they're negative because they're cut out. And I've got that semicircle. It's got a radius of 30 millimeters. So I need pi r squared there to help me out. So let's try it out. So pi r squared, I'm just going to use 3.14 for pi times 30 squared. 2,826, and it's -2. And then I would have to add all of them together. 60,000 minus 5,250 times 2. And then minus, what is that last one? 2,826. Okay, 46674. Oh, I've got all of them now. Now, here is a very important detail. Okay? A very important detail. Remember, the reason these areas are negative is simply because they're gaps. They don't exist. They're not a filled-in shape. They're a gap. And so, their area is negative. Their centroids are not negative. You only make one or the other negative. It makes sense for the centroid to be negative and make the area negative because they're not there. Now let's look at the centroids. Well, the centroid of a rectangle is right at its center, which is going to be half its height, which will be 150 millimeters. The centroid of these triangles is 1/3 of the way from the base, which since they are 150 millimeters tall, that's 50 millimeters from the bottom. Remember, all of our measurements have to be from the same point, so I'm measuring from the bottom right here. So it's going to be 50 millimeters from both of them. Now what about for this semicircle? Well, the semicircle is a bit different. It's not quite as nice. You would probably need to look it up, and you can find it in the very front cover of your textbook. What you see is that for this case, the centroid in this direction is going to be 4r over 3 pi from this top line. Okay, from the place where it's been divided in half, it's 4r over 3 pi. Woo! I know, that's pretty crazy. But That's what it is. So where is that? Well, remember we're measuring from the bottom, so I'm going to go 300 up, and I'm going to go down 4r over 3 pi. So if I do that, well, what do I get? Well, I get 300 minus 4 times 30 over 3 pi. And if I plug in my calculator, let's see what it gives me. I get 300 minus 4 times 30 divided by 3 divided by 3.14 to be pi. And I get 287.26. I'm just going to say 287. Okay, 287. Now that I've done that, though, I need to multiply them all together so I can get this last column. So let me do that, and oh my goodness, these numbers are going to be ginormous. So hopefully it doesn't just completely blow up my calculator. It's definitely going to blow up the space I have. So first I've got 60,000 times 150. So 9 million. You will see huge numbers occasionally. Okay, and then let's do 5,250 times 50. 5250 times 50. 262,500. Okay, 262,500. Make sure it's negative, because this isn't real. It's not there. Our area is negative. Our distance is positive, so this should be negative. And finally, for the semicircle, 2,826 times 287. 811,062. Negative 811,062. If you're wondering, wait a second, this is so small yet it has such a big effect. It's because it's really, really far away from this axis. The further away you are, the more effect you have. Now I need to add them all together. So I'm going to get 9 million minus 262,500 minus 262,500 minus 811,062. I get 7,663,938. 7,663,938. Okay. Now this is everything I need to calculate my centroid in the y direction, because that equation is simply y bar is equal to the sum of the individual areas times their centroid over the sum of the area. And I have both of those now. So it's going to be 7,663,938 all over 46,674. And if you're wondering what the units are, this will be millimeters cubed here on the top and millimeters squared on the bottom, because it's going to cancel to give us just millimeters, because it's just a distance. So let's plug it in our calculator and see what this gives us. 7,663,938 divided by 46,674. It comes out to be 164 millimeters upward. Okay, so y bar is going to be equal to 164.2 millimeters. Now let's ask ourselves, does this make sense? Well, that's slightly above the center of the rectangle, which does make sense because I've got more area taken away from the bottom than I do the top. Okay, it seems reasonable. If I look at our textbook, it's pretty close except for some rounding errors. So we're good. Yeah, we're fantastic. So once again, these tables are your best friends. Do not forget them. Use them in these kinds of problems. You can even use them in the resultant force problems if you ever go back there. By the way, I hope this helps you, and I'll see you all next time. Bye-bye.